Good morning, everyone. I hope you're well. So we're going to have our second session this morning on advanced neural networks. It's going to be on CNNs and transformers, and I hope you're going to get something out of it. Okay. Yeah, so we're going to continue with the second session. And so we're going to be covering advanced neural networks, specifically CNNs and transformers. So it's going, again, it's going to be an engaging session. I'll hope interaction. Sawa. I'll be asking questions and I'll hope you respond. We will do some math here and there, but hopefully along the road we will be able to learn. Sawa. Yeah, so the first one is CNN. So who knows what CNNs are? What do CNNs mean? Someone shout from anywhere. Convolutional neural networks. Yeah, that's what we're going to be studying. And yeah, so I like, when I teach something, I like giving a motivation or a background. So when you look at that image, and I ask you, what image is that? If you've looked at my slides or my notes, don't answer. If you've looked at my slides or my notes, don't answer. But if you look at that image, can you tell me what image that is? What does it look like? Yes? X-ray, what else? Barcode. And the reason I do this is because this is not the original format of this image. This is the actual image. It's a 3. But what has happened to this 3, it's a pixelated 3, but what has happened is it's been flattened. Do you get the idea? So you take the 16 by 16 and then you put them in a straight line. And so the question is, what's the difference between, what's the difference between that and this? Just visually looking. When you look at it. What tells you that this is a 3, but when you look at the other one, it doesn't tell you that that's a 3? What makes this a 3? When you look at it, okay, because of ABCD, this is a 3. What? Yes? It's dimensions, but what if it was an 8? Same dimensions, but it was this way. I get my point. Yes, I get the aspect of dimensions, but what specifically tells you that this is a 3? Don't overthink. Let me give another one. Okay, that will give you the answer. But you notice, a 3 is defined by several features. It will have an edge at the bottom, a curve, another curve, and an edge. Did you get that point? So for any 3, however I write it in some way or form, it will have some curves and some straight lines somewhere. Well, some people may not write it with a straight line, but there's an aspect of edges at the top and some curves. Do you get that point? So the first image sort of destroys that relationship, where it's that relationship of edges and curves is completely out of the picture. So, and the whole idea behind CNNs is this aspect of spatial context. Spatial context means that there's a relationship between each pixel and its neighbors. So you're not just interested in having a flat out array of 256 to represent the 3, but we want to be able to know that this pixel has a neighbor here. This pixel has neighbors here. And in this neighborhood, this forms a curve. This neighborhood here forms a straight line. Do you get that point? So essentially, when this spatial arrangement is lost, contextual information is lost. And so you cannot be able to tell this is a 3, this is an 8, this is a 7, and all that. And therefore, what CNNs try to do, they try to preserve that context, or rather to capture it using convolutions, as you're going to see. And so the reason I gave that motivation is because when you have the standard MLP, or the standard neural networks, the input is always flattened. You know, whatever input you have, you always flatten it and feed it to the neural network. Now, when you do that, as you can see, you destroy that spatial context that is very relevant. So essentially, CNNs try and, instead of destroying that, they capture that spatial context. So again, let me go back again. I've answered the question, but I'll ask it again and see if you're together. So what makes this a 3 and not an 8 and not a 6 and not a 5? What are the defining characteristics? Edges. Which specific edges? 8 has some edges, 5 has some edges. So there's an edge at the top and bottom right, isn't it? A curve, sorry, and then edges at the top and the bottom. And it will have extra features where it has some curve here and here. So it will have 2 extra curves on the left. Do you get that point? A 5 will have an edge at the top, an edge on the left, and a curve on the bottom right. So essentially, a CNN will try and capture this. So one is edges, the top part, and the other one is curves. So, and essentially, these are called features, and this is the aim of a CNN, to extract these features and to use those features to make a decision on what the image is. So essentially, this is the feature extraction phase of the convolutional neural networks. And it's kind of motivated by how we humans do it visually. You look at a certain image, and essentially you can extend this concept to any other thing or any other image, ideally, out there. So as a human being, you look at a cat and you see it has some whiskers and some fur and some ears, and it looks a certain way, and say, oh, this is a cat. There's some features you see visually. And this idea of features extends beyond numbers or handwritten digits. This is the MNIST dataset. So it's not confined to edges and curves. So if it's pictures of cats and dogs, there will be extraction of ears maybe, and the nose or the whiskers and all that, essentially. That's the running idea behind CNNs. So then the question is, how does a CNN extract these features? For us as human beings, we'll just look at things and see parts. But how do we get a machine or a machine learning model to be able to take an image and extract those features? And the answer is this thing called kernels. So what is a kernel? A kernel is a filter. It's also called a filter. And essentially, it's a small matrix. And what it does is it scans over the image. And at each step, it's sort of intuitively asking, does this patch of the image match the characteristic that I have? I get that question. So as you see, it's sliding all along the input. And at each stage, it's asking itself, does this patch match the characteristic that I am looking for? That's the intuition behind it. But essentially, it is a matrix. So you will have kernels that extract boundaries. So ideally, it can be something like a 3x3 matrix that has certain values. You can have like 1, 1, 1, 0, 0, 0, negative 1, negative 1, negative 1. And what it does is, when you have your input image, and let's say it's maybe a 5x5, 1, 2, 3, 4, 5. Yeah, 5x5, and you have values here. Let's say, for example, 2, 3, 0, 1, 5, and all that. So it will take this patch of image of 3x3, and there's a multiplication here. So this times this times that, this times that. So the 9x9 times this 9x9, and then it sums it up, and then produces a new value for the output in a given part. So whatever is happening here, as you can see, as it's sliding, it sort of looks at this patch, gets a single value, and translates that to a single value in the feature map. So this is called a feature map. This is the input image, and whatever is sliding down here is a kernel. So essentially, you can have many kernels, or usually you have many kernels that learn to extract different and various kinds of features. So you don't manually, there are standard kernels, when you're doing digital processing, like digital image processing, there are filters that detect edges and all that. But in a CNN, you do not define the kernel in and of itself or what it will do. You just define the dimensions of the kernel size, and then what we've just learned in the morning through back propagation, the kernel is learnt. The weights or the features of the weights of the kernel are learnt by the model as it's training. And so essentially you may end up with a model that has learnt different kernels of extracting different features from the images that is able to distinguish or differentiate them along the road. So yeah, the new output is called the feature map. And so some two good things to know about this whole idea of convolution. Yeah, and by the way, this process that I've just described here, you have an image, you have a kernel, and it's going patch by patch. That essentially is what convolution is. So the convolution in convolutional neural networks is this process that is being illustrated by this GIF. But some other important things that we should know is, notice as the kernel is moving, it's taking a step. That's called a stride. So a stride defines how many steps do I take at each step. So essentially, this illustration has a stride of one step, one step, one step, one step. If we have a stride of 2, it will be here, and then instead of jumping 1 step, it jumps 2 steps, 2 steps, and then jumps 2 steps, 2 steps, 2 steps. I hope we get the idea. We are together. And then we have padding. So padding is, in this picture you see the blue part, that's the actual input. That's the original image. But then we add some extra spaces around the edge and fill it with some certain values. There are different ways of padding, and maybe we will not get into that. But I would love us to see the intuition behind the necessity of padding and strides and what they do. So we are going to calculate some stuff here. We're going to do some math. And ideally, we are going to compare how the dimensions of an input image are translated by the effect of the kernel to the feature map. So we are going to compare those dimensions, the input image dimensions, the kernel dimensions, and the feature map dimensions. Are we together? So let's say, here is some math that you're going to do. And I want us to do this intuitively. So please don't cheat, don't go ahead on the slides. I want us to learn this intuitively. So let's say we have a 5x5 image, such as the one as we have here. And we have a kernel of 3, size 3. And we do not have any padding, so there's no extra space around the edges. And our stride is a stride of 1. So essentially, what will be the output length of the feature map? So this is the input image, this is the kernel, and the question is, how will the feature map look like? So I want someone to tell me, here's 5, 3, and what is the length of feature map? So we have the kernel is moving this way. So what will be the length here? Just do it manually or think about it and tell me. Remember always, when a kernel is here, it will overlay 3 by 3, and that will produce 1 point in the output. Goes to the next part, produces 1, goes that way until it reaches this edge, then goes down to the second row, so 1, and then goes to the second one, does the same, goes down, does that. So what will be the dimensions of the feature map? Don't overthink. Simple. You can literally do it manually in your head and just tell me the feature. We'll do the math in a few moments. Is anyone willing to attempt? Three by 3, isn't it? So we'll have 3 by, and how did you get to that? Exactly. So the kernel simply has 3 points in which it can lie before it gets to the edge. So the initial position, which covers 3 of them, then there are 2 left, isn't it? So that's position 1. Then the first step covers up to border 4, and then the next step up to border 5. So those are 3 points, isn't it? And since the other one is also 5, the same thing. So essentially, it will be this part of the first three, sorry, and then it makes a step and goes to the next three, that's 2, and then the third one, and it'll have reached this part. So once it reaches that, it goes down again 1 step. So again, it starts here, and since this is 3, we can simply count this is 1, and then this is 2, and then this is 3. Are we together on that? So essentially, the feature map is 3 by 3. Have we gotten that point? So 5 by 5, a kernel size of 3 by 3, and the output feature map is 3 by 3, and it's 5 minus 3 and then plus 1. You're going to see how that comes along. So let me give us another one, and you can do this one very quickly, and then tell me what will be the output feature map. Five by 5, a kernel of 4 by 4, 0 padding, and a stride of 1. Yes, you seem to have something to. You seem to have an answer. Don't fear, just say it. The same intuition that he's mentioned. 2 by 2, isn't it? I hope you see why that is. That if you have 5 here, if you have 5 by 5, you'll have 1, 2, 3, 4. So it will occupy 4 by 4. And there's only 1 row left to which it can move to. So it will be 1, 2. And then goes down. And since it's 4 and a row of 1, it will be 1, 2. So it should essentially be 2 by 2. So in this case, it becomes 2 by 2. Now, what do you notice from that? We have 5 by 5 and a kernel of 3 by 3. We get an output feature map of what? 3 by 3. An input of 5 by 5, a kernel size of 4 by 4 now, same input, a bigger kernel, and what is the output feature map? What correlation do you see there? What is happening? Yes. Exactly. So as the kernel size increases, the feature map reduces. Do you get that point? And so essentially, for example, if you have 5 by 5, okay, ideally, normally it's hard to have a 5 by 5 input for a CNN. Most will have large dimensions, 16 by 16 and above or thereabout. But as you go downwards and you're left with 2 by 2, there's basically very little you can do with that. I hope you get that. You cannot do downward convolutions. And again, convolution is not just done once. You do it several times over because you're extracting features time and time again. So, and this is where the importance of padding especially comes in and the aspect of strides. So notice as the kernel size increases, the feature map size reduces. And then notice the second thing that with our case here, with our case, okay, let me just use this example. Assume there's no padding. But notice if we have a kernel here that is going this way, somehow these central pixels are visited, so to say, more than the edges. I hope you see that. That when this kernel is, for example, here, it'll cover 1, 2, 3. Then when it goes here, this guy is covered again, so it's covered twice. And then when it goes here, this guy is covered 3 times. So it seems as you move towards the center, the central pixels are traversed. They are, so to say, convoluted more often than those on the edges. You get that? So the output feature map will actually be very concentrated with features that are coming from the central parts, but the edges are ideally comparatively underrepresented compared to the central parts. Do you get that point? So those are 2 aspects in which now padding fixes both of these. And how does it do that? One, it prevents the shrinkage of the feature map, and you're going to see that in a short while when you do another example. And then it gives equal weight, roughly almost equal weight, to the edges as to the center. So when you have some extra space here, you'll notice then that, for example, this guy, if we have a 3 by 3, this guy is covered once, twice, 3 times. And so is this guy is covered once, twice, thrice. So essentially, we are able to have extraction of features on the edges when we have padding than when we don't. And because again, remember convolution happens several times over. So we are doing a case study of a single one here. But when you have the first case of, let's say we have an input image, we do convolution, and then we have an output, and then we do a second convolution, we have another output, we do another convolution, another output. Essentially, as you go down the line, we sort of lose sense of the edges because they are very minimally captured as you go downwards. So essentially, padding aims to balance the weights of convolution, or the number of times convolution is done, but secondly also it prevents the shrinkage of the feature map. And let's do now an example where we have a padding. So the stride is the same, but we'll want to do padding of 1. So what will be the feature map? So 5 by 5, kernel size of 3 by 3, padding of 1 and a stride of 1. And by padding here, I mean, so let me explain. By padding here, I mean the thickness of this boundary. So it means all around this perimeter, I am adding 1 pixel on all sides. I hope you get that. That's what padding of 1 means. So think a bit more intuitively about how that will look like. Anyone with an answer? Anyone who's not answered? Anyone who's not spoken? This session. Anyone with any thoughts? Anyone who's not spoken? I'll prompt people to speak. Yes, have you gotten something? 5 by 5. Anyone else? You gotten something? 4 by 4. Okay. So how did you get to 5 by 5? Walk us through your intuition. Yes. Yes. Okay. Okay. So essentially, sort of you just added 2 more steps on either side, isn't it? Okay. How do you get 4? Okay. Then 4. Thank you. So something I'll add to what you said. Remember, when we pad on this end and on the other end also. I hope you see that. So there's 3 by 3. There's 5 by 5. So when you start the 3, 4, 5, and an extra one. But remember, we don't start with the image itself. There's an earlier padding we have done because we pad on both ends. Do you see that? That when we are padding, if this is our image, when we are starting, we will not start here, but we will start here because there's some padding we have done here. And that's why I clarified that when I say padding of 1, we add a boundary of 1 around the whole image. So it is 1 here and 1 here. So essentially it's +2. Ideally, I hope you see that concept. So 4 by 4 is close, but remember that the padding of 1 is all around the image. So essentially, it's simply you assume now your image is 2 more dimensions larger. So it's like you just have the 5 by 5, but then 1, 2. So it now becomes 7 by 7. Then we minus 3 because that's the initial position it will take. And then how many steps can you take from there? That's for now 1, 2, 3 for the remaining pixels, but then plus the initial position. So I hope you can get some intuition for this formula here. This is the original image plus the padding, and that gives us a sort of new dimensions of the image. And then we subtract the initial patch that the kernel sits on together. And then we remain with 4 pixels. That means it can make 4 steps. But when it makes 4 steps, we add back the initial position, which we had not counted. So it becomes 5 by 5. Now, do you notice something here? What is the input dimensions? The input dimension of the image? 5 by 5. What is the output dimension? 5 by 5. Now, do you see the effect of padding? That the feature size is not as largely reduced. There are parts where it will be reduced, but in this case it's not as reduced. I hope you can see that. So the other example I want us to do is 5 by 5, 4 by 4. Remember when you did 5 by 5, 3 by 3 with 0 padding, it got to 4 by 4. But now it gets to 5 by 5. Now if we do 5 by 5 with a kernel of 4 by 4 and a padding of 1, what do we get? Yes. 4 by 4, exactly. So it's again 5 plus 2, the full new image, 7 by 7, and then minus 4. There are 3 steps remaining, so it will make 3 steps, but plus 1 of the initial position where it was. So generally we'll have 4 pixels by 4 pixels in the output. And so you see there is preservation, a large preservation of the feature map. And so generally, these are general formula now of the relation between an input image and a feature map. And I want us to build this formula intuitively from the examples that we have had. So how do you think that formula will look like? Let me preserve these here. So if we have an input of n, let's work with one dimension here. So we have an input of n, like the one we had of 5. And then we have a kernel size of k. And then a padding of p. And by padding here, I mean the width here is p. That's what I mean by padding of p. Padding of p and a stride of s, whatever stride you pick. So first of all, how many steps can it make in one direction? So it's n, and then we do what? Someone with a thought? When we have this n, and the kernel is sitting here, kernel of k, how many pixels are remaining that it has not covered? N minus k, exactly. Are we together? So it's n minus k. So when it's sitting here, k, the pixels remaining that it is yet to cover is what? N minus k. Are we together? But now let's add a caveat. That's assuming we have 0 padding. Now because we have a padding of p, instead of n, what will we have? We have n, but then we have p here, and we have p here. So what is the whole dimension here? N plus 2p. So it will be n plus 2p minus k. Do you get that? But then we have only counted the steps it will make. There is something we've not counted. The step where it was at the beginning. So we do a plus 1. Are we together? But there's another caveat. Sorry, we have a lot of caveats, but I want us to build the formula intuitively. So this is assuming it makes 1 step at each time. Sindio? So what if it doesn't make 1 step at each time? Let's focus on this part especially. So what does that represent? It represents the total width of the whole space that the kernel will travel. And then we assume that it will take how many steps? 1 step at a time. What if it doesn't take 1 step at a time? What if s is a different value? What do we do? If, for example, let's say, let me give an example here. We have n plus 2p totals to 13, for example. And then we have a kernel size of 3. Are we together? So how many pixels are remaining here that it has not covered? 10, isn't it? 13 minus 3 is 10. Now, let me ask a question. If it's going to make one step at a time, how many steps will it make? How many steps will it make? 10. Now, if it's going to take 2 steps at a time, how many steps will it make? 5. If it's going to make 5 steps at a time, how many steps will it take? 2. So what is the intuition here? We divide by the size of the stride. Are we together? So essentially here, we divide by the size of the stride. And the reason why we did not see it is because S was 1 for our case. That's why it was not coming up. So essentially this is the formulation, but we add another caveat in the sense that this division may not always, sorry, it's not here, but it's in the notes. The caveat here is that we take the floor of this guy. And the floor simply means sometimes you will divide and get a number point something, something, something. So you take only the integer part. So for example, if we had 10 and we are taking 3 steps at a time, it will be 3.3333. So we don't have a fraction of a pixel. So we'll take 3. So we'll be able to make only 3 steps, and then we add 1, so that's 4. Are we together? So you take the floor of that. And so essentially that's the intuition behind kernels and how the CNN will sort of now extract those features from an image. But what we have dealt with is a case of an image of a certain type. And I want us to see something here. What's the difference between these 2 images? Who can tell me the difference here? One is color, the other one is gray, black and white, or rather grayscale. Now, that is for us visually. When you look at something, we can see, oh, this is color, this is grayscale. But to a machine, what does that look like? Or rather, let me ask the question differently. How does a machine represent a colored image versus a grayscale image? Yes? I can hear people speaking, yes. Okay, you are naming them. Okay, sawa. Based on the channels, but what does that mean? Kuna leakage. But essentially the channels that he's mentioned, you've heard of RGB, red, green, and blue. So for any colored image that you have on your phone or anywhere, that image will be made up of an image that is red, an image that is green, and an image that is blue combined together to create that picture that you see. So maybe you will see some parts that for blue it's a bit dark, maybe there's not a lot of blue in the image, there's a lot of green and maybe some bit of red, and when they are combined, you get this image that you see here, this beautiful image. It's a blend of the red, the green, and the blue all together. Now when you feed that image to a CNN, it does not come as one X by X or N by N as we have looked for the 3 by 3 case, but it comes as red, green, blue, each of them individually. Do you see that? So that means we will have, instead of the one kernel that we had, the kernel will have a third dimension. So sort of a sub-kernel for each channel. I hope you see that point. I hope sijapoteza mtu. I feel like I've lost people. Are we together? So let me go back a bit. So we have looked at this example where we have this is one image. Simply, it's a single matrix, and we have a kernel that spans over the image and produces an output feature map. Are we together? But a colored image has 3 of these things being fed at the same time as one image. Do you get that point? So when you are doing the convolution process or the kerneling process, we will have three parallel kernels, 3 parallel matrices forming one kernel. Do you get that point? So it will be the image is RGB, and therefore when we have the kernel for that image, we'll have an RGB kernel for each of them, and each of them will be traveling in parallel as we go along, and then those outputs are added together. They are summed up to produce one unified output. I hope you get that point. So essentially, when this guy will travel over red, this guy will travel over green, this guy will travel over blue. And as they do that, they're going together. They have the same padding, the same stride, and everything together. So each value that they get, it is summed up, and it gives one single output here. Now, are we together on that? Now, this is a case of images. Now, channels are not bound to be 3 only. This is an example of colored images. You can have an input that has many different channels. The intuition that I can give here is, for example, I don't know if it relates in this case, but for GIS guys, satellite imagery does not only have RGB. It sort of sometimes has other bands. Sindio? So I don't know if that is represented as pictures, but that's just an idea that I want to pass along. And so for each kernel, for each K by K kernel, and a set of C of them, based on the number of channels, we produce one output. Tuko pamoja mpaka hapo. Now, I'll want to add something else as we go along. On this part, allow me, I did not put it on the slides, but so essentially, one kernel ideally learns a given feature. Tuko pamoja. Now, what happens is you can have multiple kernels passing over the same image. So we have kernel 1 that passes over the image. So for example, for the colored image, it's 3 by K by K. That's one kernel. Are you together? Then we can have another kernel that is 3 by K, you know? So we have these sets of kernels that are passing over the same image, but essentially during backpropagation, they are learning different features. So one kernel may learn to extract edges, another kernel may learn to extract curves, another kernel may learn to extract other things. Are we together? Now what is interesting is the concept of channel now comes here where when we have a single image, for example, the one that we've looked at, the colored image, and we have 3 by K, a single kernel, and let's say we have X number of kernels passing over the same image. What happens is we will have a new channel of X. So we'll have X layers for the output. I hope you see that. Because each kernel is producing one. And then now we have X such kernels passing over the same image and producing X such ninis. Are we together? And therefore we will have X channels. Are you together? So the next level of convolution, we will have X channels. Did you see that aspect? So the channels across convolution are defined by the number of kernels that you have. Are we together? So that's an intuition I wanted us to get. So there are several levels of things here. There's a single one K by 1 aspect, then we replicate that by 3 or by whatever number of channels in the input. And then when we have repeated kernels, the new output will have channels equivalent to the number of kernels that we had in the convolution. And then the output dimensions will be defined by the formula that we had there. I hope you're together. Have I lost anyone? Yes. Yes. Mm-hmm. Mm-hmm. Okay. So the question will be, how does a kernel get its values? How does a kernel get its values? I think we have touched on that in the previous slides. How does a kernel get its values? Is it predefined? No. Then how does it get its values? It learns through what? Back propagation. So essentially we don't define the kernel and say this is the weights it's going to have. We simply randomly initialize it, and during the training process, the training process will define the weights of the kernel itself. I get that point. So you'll meet a certain channel has certain, so essentially I would assume if we have a classifier for green, not for green, for trees, for example, and trees are dominantly green, most probably the weights for green, the green channel, may have something that is unique compared to the red and the blue. Do you get that point? So they are not the same, they are not fixed. And it's because we are not the ones defining, it's the model that is learning the weights of those features based on the learning task. Get the point? Yeah, so they'll be different, yes. Yes. About the? Yes, yes. Mm-hmm. Yes. Kernels. Yes. Oh, the difference between the two is simply, for this simple example, it's one kernel over the image producing one output. But when you have multiple kernels, it's the same idea, but repeated several times with different individual kernels. I will get that point. So we have the same image, and this idea of the kernel is they are parallel, yes, and they give us one output, but essentially it is not sufficient to have one kernel because we want to learn multiple features. So remember, a kernel is a feature extractor. It is that thing that extracts the features that we have discussed. And so the image does not only have one feature. We want to learn as many features as possible. Get the point? So we will have multiple feature extractors, and each of them will be adapted to a certain feature that it will learn. And so those outputs then are now stacked. So we'll have the output of feature 1, the output of feature 2, of kernel 3, 4, going all the way up to the number of kernels we have. Does that answer your question? Yeah. Anyone else? Okay. So but a CNN is not made up of only convolutions. There are other layers to a convolution neural network, and we will touch this very briefly. Then we're going to see the advantages of convolution over others. I see time is much spent. So there are other types of, so that's essentially, so when you're saying a CNN, a convolutional neural network, the convolutional in CNN is whatever we have discussed, all that concept of those feature extractors. But that's not the only thing. So there are other types of layers in our CNN. So the ones that we looked at are convolutional layers. So there are pooling layers and fully connected layers. Now the pooling layer is similar to convolution, but the only difference is it is an operation. It is not learnt. It's not a matrix that we have to learn its weights. It's a matrix that has fixed weights, or not fixed weights as I will say, but it's an operation that does something, and we're going to see very briefly what that means. And its main aim is downsampling after the convolution layer. And some of the common types of pooling are average and maximum. And then finally, the fully connected layer is now a neural network, which is fed with the flattened output of the convolution and pooling layers. So essentially, it receives the learned features, and you're going to see that visually. So I just want you to have that at the back of your mind as we look at it. So this is what pooling looks like. So we have done convolution, for example. There we have 5 by 5, a 3 by 3, and then we get a 3 by 3 or a 5 by 5 or whatever it is. Basically, what pooling does is there's max and there's average pooling. So for example, it's 2 by 2. You'll meet oftentimes it's 2 by 2, or you can define other sizes. But you'll take a patch of 2 by 2, and then for the 4 of them, if it is max, it picks the maximum among those and outputs that to this part. If it is average, it takes the 4, does average of the 4, and then outputs to the output. Are you together? So you do convolution, the output of a convolution, you do pooling. So it'll either be average or maximum, at least those are the most common ones. And the idea is it preserves detected features. Sorry, I think there's a confusion here between max and average. So I think max preserves the detected features, and it is the most commonly used. But for average, it downsamples the feature map. But for all of them, they downsample the feature map. So it's a way of, we are doing convolutions, yes, but as we go along, we want to be in a way strategically reducing the feature map, but at the same time preserving the detected features. So that's what pooling basically does. But then eventually, after all this convolution and pooling, the output now, which is ideally, if you think about it, the outputs of convolution and pooling, what is that? What does from what we've discussed, what is the work of convolution, or rather, what is convolution? Feature extraction. Are you together? So now the neural network is fed with features that have been extracted from this image. Now, I hope you see the contrast between feeding the raw image directly to the neural network, to the fully connected layer, as opposed to, first of all, having a convolutional layer and feeding that output to the neural network. You're going to see that in a brief moment. When it's fed directly, the fully connected layer has by itself to learn the features. Together. But when we have convolution, the features are learned, and then when it is passed, the work of the fully connected layer is to, based on these features that have been learned, to make a prediction of whatever task you have. If it's digit classification, if it's object detection, or whatever it is that. And so this is a full picture of how it looks like. And these layers can be repeated of varying dimensions and all that, but this is another one. So this is input, and then you do convolution. And ideally, if you look at this image, for example, you see the input here is 1. Sindio? But the convolution here, if you count 1, 2, 3, 4, 5, that simply tells us that there were 5 kernels. Did you get the idea? There are 5 kernels, and therefore we have 5 outputs that are there. And then after that, we do max pooling, and here there is nonlinearity. I'm forgetting, what do we call them? Activations. So they are activations. So after every convolution and pooling, there's activation. That's a nonlinearity here. So we will not touch that because it was handled in the morning. Then we do another layer of convolution, and then we do another max pooling, and then nonlinearity, and that can be repeated as many times. So you can have a broad model, and also you sometimes can have depth in terms of how deep the convolution is. And then after that, the learned features are referred to a fully connected layer, obviously with nonlinearity, and then the predictions are made. That's a CNN. That's a convolutional neural network, and it's the same image here. Input, and then channels for layer 1, layer 2, and all that. So the next point that I want us to look at is then the model complexity of a CNN, and why a CNN ideally. Why a CNN? Why not go directly to the model itself? So I want us to count the parameters layer by layer to get some intuition of why a CNN came up, or the intuition behind it. So let's take, for example, layer 1. If you have the notes or the slides, you can follow along. The image is not as clear. But let's say we have layer 1, this convolution. The convolution has a kernel of 5 by 5 by 1. We assume a padding of 0. The input is 28 by 28 by 1. The number of kernels is 16. And then the output. So we are not going to be doing that formula. It's pre-done for you. 28 minus 5, 23 plus 1, you get 24. All together. So that's the output. And then we will have 16 kernels. And because we have 16 kernels, then notice that the number of channels in the output is what? 16. It's 24 by 24 by what? By 16. Now the question is, what does the model learn? Again, what did we say in convolution the model learns? The kernels. Are we together? So essentially when we are counting the parameters, we are counting the parameters that the model will learn at this convolution step, which is the weights of the kernel. Then the question is, how many parameters are in this kernel? Times 1. Thank you. But I'll add a caveat. Remember, after every convolution, there is a bias. There's a bias that is added. So every kernel has a bias attached to it. So each kernel is 5 by 5 by 1 plus 1. There's a bias term that is there for every kernel. All together. Just like in a neural network, you'll have a single node. Sorry, the word is running from me. The single neuron, and each neuron has a weight and a bias. All together. So essentially, the weight for this case, the kernel is 5 by 5 by 1, but it has a bias term. So it is 5 by 5 by 1 plus 1. So that's 26. All together. But how many kernels do we have? 16. So it's 26 times 16. So the number of parameters in layer 1 that the model will learn is 416. Are we together? Are we together on that point? Then you go to layer 2, the pooling layer. How many parameters are here? Or rather, let me ask the question differently. What is learned in the pooling layer? We do not learn anything in the pooling layer. Are we together? Remember, it is a fixed operation. We'll either average or we'll either take the max. So there is nothing that it learns. There are ideally no kernels. It's not a kernel. It's size 2 by 2 by 1, but it's not a kernel. Are we together? So the number of parameters that are learned in a pooling layer is 0. Let's do convolution layer 2. Kernel size of, now notice again, the number of channels in the output of layer 1 becomes, the number of kernels in layer 1 defines the channels of the input for layer 2. So remember we had 16 kernels. Now the input, the kernels here on this side are 16. Not 16, sorry. The channels for a single kernel are 16 because we must have a sort of sub-kernel for each of the 16 inis to aggregate them to one altogether. And it's because the input is 12 by 12 by 16. But then those 5 by 5 by 16, we have 32 such of them for layer 2 altogether. Now the question is, how many parameters do we have? What are the parameters of a single kernel here? 5 by 5 by 16 plus 1. What is the number there? Do the math. 401, exactly. 25 times 16 or 100 times 4. And then plus 1. And then how many what is the number of kernels? 32. So 401 times 32. So that gives us 12,832. And then pooling layer 2, how many do we learn there? 0 altogether. So parameters are 0 there. And then the final fully connected layer. So a fully connected layer has an input of 4 by 4 by 32, and this will be flattened out. So it's 4 by 4, 32 of them, but then they cannot be fed like that to the layer altogether. So they will be flattened out, the concept we began with at the beginning. So 4 by 4, that's 16, and then times 32 altogether. Now, how does a fully connected layer look like? I think Cedric sort of handled this, but we didn't do the parameter count. So essentially you have input here. In this case, it's 4 times 4 times 32 altogether. Now, and then we have a single hidden layer for simplicity's sake. It can be several number of layers, but here we have a hidden layer that has 64 of these altogether. So this is 64. And then since we are classifying handwritten images, the number of digits is 10. Tuko pamoja? So this is 10. Now, for a fully connected layer, what is learnt? Weights and biases. So essentially, and because it's a fully connected layer, what does a fully connected layer mean? This single node is connected to every other node in the next layer. That's what a fully connected layer means. So here we have the weight of this guy and the bias term all together. So it's this to this. So this 64 times this, 64 times for all of this all together. And then we have then 64 and the 10 ones, all of them. That's what a fully connected layer looks like. So what will be the parameter count? We just multiply all those things. So it's 4 times 4 times 32, which is the input altogether, plus 1 for the bias term, times 64. The bias term for all the 64 of them. And then plus 64 plus 1 times 10 altogether. And that gives us 33,482. There's a reason we're doing all this math. It's all going to make sense in a little moment. So essentially, for such a network, we will have, when you sum all them up, two convolutional layers and a fully connected layer, FC0 is 0 because it's simply flattening. So there's not much there. So it's 46,730. I hope you get that number. Now, let's ask ourselves a question and compare something here. The CNN, the convolutional layer, the first convolutional layer in a CNN, the math we did for our case, had 416 parameters for it to learn. Now, what if we were feeding the 5 by 5 to a single, to a standard MLP directly? We flatten it out and we pass it out, and it wants to learn those features. How many parameters will it have to learn? So if you flatten, the input was 28 by 28, the kernel is 5 by 5. So if you flatten 28 by 28, you get what? 784. So the input, the first layers will be 784. But then we have the output. So remember, the first input we had 28 by 28, and then after the first convolution layer, the output was 24 by 24 altogether. Now, if we are to have the same special output of 24 by 24 by 16, that's 9,216. So the first layer there will have 784, then the second layer will have 9,216. Then, that is for convolution 1 only. If you count the number of parameters, you get what? 7,000,000 234,560. That is one step equivalent to what you're doing in convolution. But convolution only learns 416. That is 17,390 times more parameters, and that is only for the first layer. Now think about the second layer, and this is a very simplistic convolutional neural network. Many of them have many layers and many kernels, more complex. I hope you see that point. Now, this is where the advantage of a CNN for spatial images shines, in the sense of what you need to learn is small compared as if you will go to a vanilla MLP. And the reason for that is a CNN does something called weight sharing. So this is, we are concluding here, and then we do the next half, sorry. So a CNN, you see, an MLP, when it has 28 by 28, 784 of them, and then it does 24 by 24 by 16, that 9,000, what it's trying to do is, it's trying to learn the image exactly of where things are in that image. Look at that point. But what a CNN is doing, it is not learning where things are in the image, but it is learning how to detect that thing in the image. And that principle of detection will apply to any other image. So essentially, it is learning how to extract features instead of like learning the features themselves by itself. Do you get that point? And so that's the aspect it's called weight sharing, and that makes a CNN very, very effective in images and special stuff. So concluding, CNNs, they learn a set of shared feature extractors called kernels. This allows them to be very efficient in terms of parameters and complexity, and these kernels also capture the spatial context of images. Thus, they outperform standard MLP networks for images. So that has been CNNs. And you can do research on now. There are standard models that have been defined, things like EfficientNet, MobileNet, and all those kinds of network. Research has been done on them. I largely work with EfficientNet. I'm not looking into MobileNets, but interesting architectures. You can have a look at them. So that has been the first half. Allow me to rush into the second one, and then we'll finish. Sorry, it's advanced neural networks, but I hope you're getting something. So, are we together up to this point? Are our heads okay? I hope they are not on fire. Yeah, so transformers. So I think all of us have used a transformer. Essentially everyone here has used a transformer. But the question is, we have looked at spatial images, but the question is, what about other forms of data? Are there other forms of data that require a kind of architecture tuned towards the data? And the answer is yes. There is sequential data or temporal data. And sequential data or temporal data is defined by the fact that there is an ordering. There's a dependency in terms of time. Something comes before or after the other, and you cannot switch them up. In standard machine learning, you'll find sometimes when you have like features and inputs, you can sort of, the X, you can, it doesn't matter the order in which you place the inputs, for example, for your table. If you have a data frame, all together. Columns are your features, and then rows are your inputs. So for standard one, it doesn't matter whether index 1 is a given input or it's position 100. But when you come to sequential data or temporal data, data that is defined by the sequence, that is the steps or the aspect of time, order is very important. So just as we have seen images have spatial information, that is information about space, and when we alter that data, it affects the model and we lose some certain of information. So also in sequential data, there's an aspect in which we have to capture the temporal aspect or the order in which the data comes. Are we together? And I'll motivate this with a given example. So this is an example that came to mind. So look at these sentences. Only she told him that she loved him. Then she only told him that she loved him. She told only him that she loved him. She told him only that she loved him. She told him that only she loved him. She told him that she only loved him. She told him that she loved only him. Now, is there a difference between those sentences? But is there a difference in the number, the words? Are the words any different? What brings the difference? Order. Shifting only affects the meaning of the sentence. So when you're dealing with sequential data, we must be able to capture that, yes, this sentence has these words, but only is appearing at the beginning and not after, not before loved him at the end. Did you get that point? Because the moment you change where only comes in, the meaning changes. That's the aspect of temporal or sequential data. Now, a second one, just changing the position of the word only changes the meaning. Now, another example, and we're going to get two principles from this. So, I hope hakuna utakona leakage, but let's do this. Slides are availed and notes. So, kama umepitia, you may have a Mwakenya here. But yeah, the analysts warned that the bank will be broken by, complete the sentence. By recession, By what? Sorry. Robbers, So, we are saying the analysts warned that the bank will be broken by recession, by robbers, by thieves. So what is the bank in that sentence? A financial institution. And who are analysts in that sentence? Financial analysts. But what if we say the analysts want that the bank will be broken by floods? It's a river bank. And the analysts are environmental analysts. They get the context. So the meaning of analysts and bank is defined by what? Floods. Do you get that point? So there's an aspect of disambiguation. And the second example, but if the analysts want that the bank will be broken by thieves or by recession, then the analysts are security or financial analysts, and the bank is a financial institution. So that single word, whether it's floods or thieves, changes the whole meaning of banks and analysts. And these are two concepts that are principal motivation for the architecture of the transformer model. And the first example highlights the semantic importance of our word's position. That is position, that's one. The second one is disambiguation, where the meaning of a given word is given its meaning by another word in the same sentence. Get that point? So it says here, where the meaning of a word is informed by its context. Bank can be a financial institution or the edge of a river, depending on other words that inform its meaning. And you're going to start with the last one, and you're going to see how that comes through. But before there was a transformer, there were other models. There are two architectures, and they're still in use today in different contexts, but they largely motivated the transformer model. So the two are recurrent neural networks and short-term memory. We'll not go into in-depth into this, but we'll give a brief overview into some of the concepts that motivate the architecture of that. So an RNN, Cedric touched on feed-forward networks, and he mentioned that feed-forward networks are networks where information only flows forward. It never goes back, or rather there's no recurrence altogether. A future step does not inform a prior step. Do you get that point? The information does not flow backwards. But what a recurrent neural network does is exactly that. So this is an RNN. So there are two dimensions of being an RNN. It's a normal neural network, but with a simple caveat. You have input and output, then you have the weights here. But at each step, let me think about how to put it. Let me just read it. So RNNs are like your normal neural networks, but with special features, recurrence. Each input is indexed temporally. So we have xtn minus 1, xt plus 1. And at each step, the network also has a hidden state. So inside the network, there's something called a hidden state. And it stores sort of the history. It is fed with two things. So at each step, we feed it. So let's take this is the initial step, but at every other subsequent step, we feed it the input at that temporal step and the history of the previous step. Do you get that point? So it is informed by two things, that we will always have the input, and then sort of the previous state informs the next state altogether. And this is the idea where it tries to capture what it has seen in the past, and based on what it has at the moment to make an informed decision. So it tries to capture that aspect of prior things that have happened. And so it is the same network essentially, but its state changes across time due to change in hidden state. Especially, that is space-wise, the network on the left, especially the network is on the left, it's the same network, but you can unroll it. This is called an unrolled RNN. An unrolled RNN is where you unroll it across time altogether. It doesn't mean that the model is repeated several times, no. It's simply saying the model you have at step T is a bit different from the model you have at step T+1 because the history, the context has changed altogether. So you can unroll it temporarily across time, but it's the same model, only that its state is changing with time at every step in time. And so the shortcomings of this is, and you can study this more, is that model compression. So if you have a very long sequence, and you can see this in this formula, the whole aspect of back propagation and that, you see as you go along this way and you get more and more steps going forwards, you will realize that these guys that were here, the history that was gotten from here is more and more growing insignificant as you go across. And the most recent history is amplified. Now, in the example that we gave, for example, the analysts want that the bank will be broken by thieves or by floods. Now, the word floods gives meaning to analysts. So if we have forgotten what has happened in the past, the future is also affected. So when the sequences grow very long in RNNs, it tends to forget memory compression and also vanishing gradients. There's something called back propagation through time, BPTT. It's a special kind of back propagation suited for recurrent neural networks, where we not only have to do back propagation, like from the future layers backwards to the previous layers, but we have to do it across time. It's like we are time traveling to the back and doing back propagation on that across time. So it's a very complex process, and it suffers from vanishing gradients, especially if the NINI grows very, very long and complex. So the other thing also is that it is sequential in nature. Before I get to step T, I must cover step 1, step 2, step 3, step T-2, step T-1, and then do step T. So, and therefore, we cannot parallelize operations there. So to resolve some of these issues, the LSTM was invented. That is long short time memory. It handles the issue of vanishing gradients better than vanilla RNNs. And although it was designed to handle historical context, for also long range, for very long range, it also suffers the same problem. And earlier context degrades because the model loses a bigger picture, and also does not fix the issue of the sequential bottleneck. And the key inventions of the LSTM is that they added gates. So you have a forget gate, you have an input gate, and you have an output gate. And you have a memory running across all the cells. So a forget gate will, for example, learn what and when to forget some history. The input gate will learn, like, what to add to memory. The output gate will learn what to pass to the next layer. So all these gates were added sort of to be able to manage that aspect of memory compression. So remember our earlier sentence. And so even with LSTM, the shortcomings were still the same. But in our earlier sentence, the analysts want that the bank will be broken by dash. What resolves the meaning of analyst and bank is the word after by, and that is either floods or thieves. In essence, floods or thieves attends to bank and analyst. And so what helped us resolve the meaning of analyst and bank 9 and 5 words later is the word after by, which is the word floods or thieves. And essentially, when we came to that, we did not have to compress the history. We only had to look back or look forward and see how the words correlate to each other. And this is attention. So attention came in place to sort of try and mitigate that issue in LSTMs. Did you get that point? So we've had RNNs, we've had LSTM, and then they add this concept of attention in LSTM. And the whole attention is simply, instead of me trying to always, compress the history, why don't I just look back directly? I am here at I'm here at floods, and this way, don't I just look back and see, oh, there's analysts, so they are related this way. So it's sort of some kind of lookup, so to say. And this technique was added to RNNs and LSTMs to help resolve the long context bottleneck. And it worked, things improved, but it was still an issue because it was sequential still, the RNN and the LSTM. So some of these memory issues we've resolved, but it's still very sequential. And so what if attention is all you need? And that's a question that the authors of this paper had. This is a very groundbreaking paper in 2017. For those of you who've used ChatGPT, Gemini, DeepSeek, it sprang from this single paper. Researchers at Google took the RNN and the LSTM, played around with it, and then they decided to strip away all recurrence. And they simply said, what if Koistoriote, all you need is what? Attention. So what if attention is all you need? It's a beautiful paper. I'll recommend you to read it. It has some heavy stuff, but it's a very nice paper to read. So what if we just drop recurrence and we just have attention? So what is attention? And that's a burden of what we'll study in transformers. There are many other things about transformers which we'll not look at, but we'll zoom in on attention, and when we have that, we will be home and dry. So let's take a case scenario. How many of us have used Google? Okay, obviously it's a rhetorical question. So when you're using Google, what do you use Google for? Search, sindio? Now when you are searching, what must you have? What must you have? Well, there's internet. Let's assume you have internet and you have the browser and you've opened Google. What do you need to search? Yes? What do you want to search? Sindio? And what can we call that? So there's something you want to learn. All together. A prompt, you can call it a prompt, or whichever other word, all together. So that's the first thing that you have. So when you, for example, go to a Google search page, and you have here, you have your search question there, and then when you press enter, what do you get? Get what? Results. Sindio? And you'll have the header and the link, and then some small snippet on what's the content of each page. Sindio? Now, what are these parts? What are you searching for? That's your query. All together. So, for example, here I was searching for attention mechanism. So I have a query I want to learn. So I'll put that to the search bar and tell Google, hey, tell me about what? Attention mechanism. All together. Now, when I press enter, I get results. But the first thing I get here is a key. It is not exactly the thing that I want, but it is labeled in a way that it gives me some information about the full content. All together. It's a key. It's like a dictionary, key values. All together. So you get a key there. And I'm going somewhere with this. I know some of you already know where I'm going, but let's follow along. And then finally, when I see a label, it has some value, the content that I'm looking for. All together. So I will have, every key will have a value. So I have a query, but every key has a value attached to it. So for example, for this Wikipedia, the key is attention machine learning. I click on that, open the page. I get the full value, the full content of what I'm searching for. All together. Now, attention sort of works in the same way. It may not be a one-to-one relation, but I'm using this to motivate how attention looks like. Sorry, this I didn't expect it to be this dark, but it's okay. Now, attention works in the same way, in the sense of we have a query, a key, and a value all together. Now, every word in the sequence has a query, a key, and a value all together. All together. Now, the only difference with attention is, unlike Google, where we just have one query and get many results, we are doing a query against every other word for every word all together. So you have the same sequence here, and we are asking a question, okay, yeah, how relevant is this to what I'm looking for, based on the key and then the value attached to it. So some will be stronger, some will be weaker. And that's, for example, for Google, when you search attention mechanism, Wikipedia comes up very strongly because its key and value is very related to the query that you have. But along page 20, you'll find some other small nini there that has maybe some attention about psychology and all that, which is really not related to what you have, but there's some, maybe the word attention is what captures it. I hope you get that point. So that's the same way it sort of works. So we do this across every pair of words. So every word, and this, for this case, it's self-attention. So self-attention simply means it's attention of an input against itself. So every word in the input against itself. We calculate that for every. And I'm going to see how that looks like in a brief moment. So the query key and value are learned matrices. So again, this is a concept of learning. So the model will learn this during training, and they're represented by Q, K, and V respectively. So this is an example of so this is a visualization. There's a tool called Bertviz, Bertviz. I think maybe I'll share it if it's not there. But BAT is a transformer model. So you can feed it a sequence, and then it can generate for you queries, keys, and values. So this is an example of a query matrix that the model has already learned. So this is something that it has already learned. And if you look at the sequence here, this is our sentence altogether. And then these are the query values for each word. Now, the query is, as I said, this is a matrix, but for each of them, it is a vector of a given dimension. So every word will have a query vector, a query vector that has a certain dimension, and for this case, it's 64. So every word will have a queue of length 64 altogether. Every word will have a queue of 64, and then they have been concatenated. And then you see the values. This is a heat map, because the numbers will be too small for you to see. So it's a matrix. That's what, for example, a queue looks like. And this is how a key looks like altogether. So every word has Q, K, and V, and then this is just the key for every word. But now the question is, and this is V as well, but then the question is, therefore, if Q, K, and V are matrices, how do we get similarity between two matrices, namely Q and K? Or let me ask the question a bit differently. We have done vectors. How many of us have done anything to do with vectors in math? How do you get similarity between two vectors? How similar two vectors are? Or how close they are to each other? Yes? You have two vectors, and you want to see how close they are, or the angle between them. Cross product, cosine. You've heard of cosine similarity? Or the dot product of two vectors? You've heard of dot product in vectors? Now that's where this idea becomes very important. You know, sometimes when we were in undergrad, I did CS, and we were asking ourselves, so all these stories about linear algebra and matrices, where will we use them? Then I came to meet these things here. So essentially, we borrow the same idea. So a dot product, there's a concept called cosine similarity, and it's a dot product of. So but these guys are, I will say, normalized for cosine similarity. But in this case, we don't normalize them. That is, normalize simply means we compress them to size 1 altogether. So you might have vectors that are varying in range. So we compress them to 1, then we do the dot product. That dot product will tell us how close or far apart they are from each other. Now the same idea applies here, only that we do not compress them to size of 1. So dot product is used to estimate similarity between two matrices. And so you notice we multiply Q by K, and yes, we do simply transpose essentially here, and I think Cedric has covered that a lot, so we'll not get into back why we transpose this matrix multiplication. So this is very close to cosine similarity, only that the matrices are not are unnormalized. Sorry, and so we simply have a question, and we have several keys, and we want to see how relevant are these keys to the questions that we have, to the query that we have. So we multiply this query with the keys and get the values out of that altogether. Then that will tell us, hey, this is a very relevant, this is not so relevant, this is very relevant, this is not relevant. So that's intuition behind this operation. But then, remember, because we did not scale it like in cosine similarity, and sometimes these things can grow very large, and you can get numerical issues, numerical instability, where maybe the number becomes so large that it cannot be represented. We divide by the square root of dk. Dk is a dimension of the key, which is apparently also equal to query and vector. So it's this length, 64. So the vector that is 64, that's the dimension of the embedding dimension. We'll also not get into that. But essentially, after getting this product, we scale it so that the gradients do not become so large. They do not explode. There's exploding gradients and vanishing gradients. And so when you do that product, visually this is how it looks like. And I hope you can appreciate that now it's a square matrix because of the multiplication. So we have the outputs, the raw scores of Q times K transpose divided by square root dk. So, and then we perform softmax to scale it to 1. We perform softmax to scale it to 1. So you notice here the ranges are from like 0 to 6 or 8. Sometimes the range can be very dynamic. So we do softmax, and softmax simply tells us that for every row it sums up to 1. So every row sums up to 1. But then, so these are the attention weights before we get the value. And then, now since we want to get the value, we simply multiply the attention weight to each of the values. So after softmax, after scaling, or after putting them in the range of 0 to 1 or them summing up to 1, we then multiply that with the value matrix. So it's like, we have Wikipedia, that's the highest. Then we simply say, hey, now since this is the highest, put more weight on whatever content Wikipedia has. We want to read more from that. So you multiply it with V. And so this is how it looks like. This is how the whole thing looks like. So you have the query matrix, the key matrix, and the value matrix. We do query times transpose of KT, essentially similarity, and then we divide by the query size, or rather the dimension, the embedding dimension. This is the aspect of masking. We may not get into that because of time and also a lot of content. Then we multiply by V, and then we get the output. That's simply attention. That's how attention looks like. So that's how ChatGPT and all these other models at the core operate. And I hope I still have your attention. I hope I still have your attention. We've done a lot of math here. Now what we have looked at is a single head of attention. Now get me right. Now remember what let me borrow from CNNs. So we've seen in CNNs you can have a kernel that can learn how to extract a given feature from an image. A single kernel. But then you can have multiple kernels with each of them learning different features. Now it's the same thing with attention. So every set of Q, K, and V is called a single head of attention. So it's a set of Q, K, and V that are learned together. Now what happens is you have multi-head attention where you have multiple sets of Q, K, and V. So you have Q, K, and V, Q, K, and V, Q, K, and V, Q, K, and V, multiple heads of that. And essentially the idea here is that each head learns a given feature across the tokens. So the tokens is your input sequence. And so we capture more ideas. So you may meet one head of attention learns to capture positions. So like the only part, only she said, she only said, she said only. You get that point? So you'll meet one head will learn to look at the position of words and give them weight. Another head of attention will learn to correlate the meaning of words. It learns that, when we say analyst said that the bank will be broken by thieves, thieves gives meaning to analyst and bank. So different heads learn different aspects of the data. That's the idea here. So just like what we had in CNNs. And so, sorry, this is a very large block of text, but we are finishing up. So if you have the image, you can follow along. I'm going to make a few points as we summarize and close. So how many of us are able to access this image? You're able to see it? So we are going to discuss a few points very briefly. So whatever we have looked at is the whole concept of attention and of disambiguation, words giving meaning to other words in the sequence. Now there's a first concept of position that we did not look at. So because this thing is a matrix, it has no sense of order. We can shift up things and the model will not be able to know. So then how do we encode position and give a sense of position to those words? So if you look at this model, this is the image from the attention is all you need paper, the transformer model. So when you have your text, when you input it, there's this thing called, so you have the embedding here, you get the embeddings. Again, we'll not look into that. All these things that I'm saying, we'll not look into that. Please go and study for yourself. Sasa. Now, after you get the embeddings, we have something called positional encoding. So what positional encoding does is it uses sinusoidal functions, cosines and sines. And in a way, it adds the contextual information of position to the embeddings. So as the embedding goes ahead, inside it, the meaning, or the position is embedded into the embedding. So you don't have to tell the model, this is the order or all that. Inside the vector itself representing each word, it contains information about position. That's where position encoding comes in. Now, the second thing is after every layer, here multi-head attention feed forward, masked multi-head attention, and then also cross attention on this other end. After each layer, you find something called add and norm, add and norm, add and norm, add and norm, add and norm. So what is that for? The idea is we take the input here, we pass it to the multi-head attention, we get the output, simply the process we've looked at in depth. It is simply this one part only. But once we get the output, we add back the input that we had before doing attention. All together. So it's called a residual connection. It's called a residual connection. And the idea is to stabilize training. And then we do normalization. So you add the residual connection. So it's simply X. So let's say we have X. You do attention of X, get the output, then the attention of X, the output of that, you add X again. And then you normalize altogether. And the idea is to stabilize training. The values there can diminish or grow so bad, so you just add it back to stabilize the training. Then notice that each of these blocks, it is written an X and X. So essentially the idea is you have attention, and then you have a feed-forward network. That is one sort of node. And then that is repeated n times. That's what n times mean there. So you'll have 1 time, 2 times, 3 times. So you do attention, feed-forward, and then again attention, feed-forward, and then attention, feed-forward, up to n times. So each block is repeated that way. And then, so that means the output of this block feeds the input of the next similar block. And ideally, again, each of those blocks is learning different features from every other block. And then notice, so these are just points that I'm giving, we are finishing up. So notice on this side, we have one block here and another block here. So this is called the encoder. This is called the decoder. The encoder-decoder architecture is not unique to transformers. It's been used in other contexts, RNNs and LSTMs, and many other places. But the whole idea is the encoder takes input and compresses it to something called a latent vector. Sort of compresses the meaning and the context to a standard fixed dimension vector altogether. And that happens for a lot of models. If you've used diffusion models for image generation and all that, they take in your phrase and then they compress it to a latent vector. And then essentially what a decoder does is, if it's an encoder-decoder architecture, the decoder is the other side, is that it'll take that vector and try and decode it, and then whether it's translation, it'll now translate that either from English to French. If it's image generation, the latent vector will tell it what kind of image it is. And conceptually, okay, this is an idea that has come to mind. Conceptually, what you'll find is, for example, here you'll pass a word here, you know, and so how, okay, let me deviate a bit. So how latent vector or latent spaces work is, you have this idea where we have meaning of words or of pictures and of sounds as human beings, but machines may not as easily understand them. So what we do is the encoder takes those things that we understand, and through this process of learning, when the model has already learned, it learns to translate them to a given dimension which encodes certain kinds of information. Now it does not do that only for words. So let's say, for example, it's English and French. So it will learn to translate both English to this dimension and French to that dimension, so that they have a unified dimension in which they are interacting. And ideally, these are just matrices. So when the encoder has taken an English phrase and encoded it to the latent vector space, then what the decoder does is, it takes that context and then goes now back to French. Get the point? Because it's a shared space. And it's the same thing for image generation. It'll take the words, give them to latent vector space, and then for the image, it'll use that context to generate images. So again, I'll not get into that. Cross-attention. So we've looked at self-attention. Self-attention is where you have the same input having attention against itself. Cross-attention is where you have one sequence having attention against another sequence. So if you're translating English to French, you will have one side is English attending to a French phrase altogether. So they'll have different parts. That's cross-attention. That's where the encoder and decoder meet. So the final output here is fed here, the query and the key, and then the value comes from the decoder. Next two things, multi-head, masked multi-head attention. So the work of a decoder essentially is to generate. So for example, when you pass a prompt to ChatGPT, usually see it generates word for word. So when you're training a decoder, you don't want it to see the future. You want it to learn how to predict the future. So when you're feeding it the sequences, you mask it at each step. So you only reveal previous information only altogether. So if it's learning to generate text, for example, let's say for example transformer. Transformer architecture was introduced by dash dash dash. So if you have a text introduced by Google in the year 2017, it is a current model and all that. So you just show it a part of it and let it learn how to generate the next part. You don't show it everything. But for the encoder, you show it everything. Get the point? So that's a part of masked multi-head. And finally, context window. So how many of us have ever used ChatGPT and then you have a very long conversation? And then it reaches somewhere, it starts forgetting things you told it at the beginning. Ever experienced that? So what is that intuitively? And this now becomes very important of what we have learned. So essentially, the query key and value matrices, they have a certain length of words that they can have at the same time. Remember we said attention is like lookup. So it has a maximum number of words it can look up at the same time. So if the input or the conversation grows beyond that, whatever context or whatever information was put in first is pushed out. It's like a fast in, fast out. So itakuta the new context window now is not, the attention is not looking at vile vitu za kwanza. It's not looking at the freshest information because your conversation has exceeded the capacity of the attention block. Get the point? So when it's doing the lookup, it will not be able to look up at prior information. So that's what happens here. So I'll not get too much into this. I'll just mention it in passing and then we'll finish. RNNs have ON time complexity and ON space complexity. So sorry, this statement is wrong. I did not update my slides. The updated information is on the notes. So essentially, takeaways: CNNs capture spatial features through a set of learned filters called kernels. RNNs and LSTMs process sequential data step by step, saving history and state, but they suffer massively and along context and are sequential. Transformers are sequential models as well in the sense of generation, but they use attention only, and this attention allows it for parallelism. So essentially, when we talked about multi-head attention, each head of attention can be done in parallel. Look at that point. So that's why it beats RNNs. But if you need longer sequences, you can scale the attention block size, and that's your context window. So advanced neural networks are informed by the kind of data and the task they aim to achieve. So a CNN is informed by the fact that images have spatial context. So you have a model that is able to handle that kind of data. The transformer model is informed by the nature of sequential data and how that operates. So data informs the architecture of the model. It is embedded in the very math, as we've seen in CNNs and in sequences. So it's important to understand the building blocks so that we are able to appreciate what these architectures do and where they behave as they do. And I'll encourage you to have fun exploring more advanced stuff. You can check out more stuff out there. So I see it's already 1:26. I had hoped you could play a Kahoot, but time is gone. Tunaweza fungia hapo ama tutacheza Kahoot. Eti? Tufungie hapo. Sawa. It's okay. Anyone with any questions? We've learned something? Sawa sawa. Let's meet in the afternoon for the practical. Sorry, time has extended much.